Welcome to Algebra 2, Unit 9, Section 2, Characteristics of Normal Distribution. When we finish this lesson, you'll be able to recognize characteristics of a normal distribution and use mean and standard deviation to completely describe a normal distribution. So, we're going to consider the distribution for batting averages for the Snappers baseball team that we did in the last unit. Recall that the distribution is symmetrical, unimodal, and somewhat bell-shaped. Distributions with such characteristics are frequently considered to be normal distributions. The density curves for these distributions are called normal curves, and normal curves are special as the mean and standard deviation provide a complete description of the distribution. So here we have on the left a normal curve. And there's parts of this curve that we want to discuss a little bit. So concave parts look like this here, right? That they're curved up. So this would be a concave point here, and here we would have a concave point here. The concave up, let me rephrase that, concave up. Concave down would go from here to here and also from here to here. So those sections are called concave down. And these points here where it changes, all right, those are called the inflection points. And in regards to this course and what we're doing, we're not going to worry about those. Okay, those are typically found using calculus, and so we're not going to really mess with that at this time. All right, so we're going to talk about the distribution of team batting averages for the St. Louis Cardinals for the 50 years from 1964 to 2013. And these can be considered approximately normal. The mean batting average for these years is 0.2637, and the standard deviation is 0.0096. So what would the median be? Well, since this is a normal distribution, and if we have a normal distribution as well as I can draw it, typically what you're going to see is the mean is right there, but so is the median also is the same amount. So we would say the median batting average would be equal to 0.2637, and the standard deviation would be the same. Okay, so to determine a scale when drawing a normal curve, it's important to note that the mean value corresponds to the peak of the curve, and that the points at which the curve changes from concave up to concave down are approximately one standard deviation from the mean, and those are the inflection points. Okay, so we're going to use the mean and the standard deviation for the St. Louis Cardinals batting average data to label the three middle tick marks on the scale for normal curve below. Okay, so explain how we choose to label the scale. All right, so in this case, the mean is at this peak. So the mean is 0.2637. So this would be, let's move this up a little bit more. So right here would be 0.2637. So each of these marks are exactly one standard deviation away. So if we come over here and we use our calculator, so we have 0.2637, and we're going to add 0.0096, and it helps if I have the right number in here, so I'm going to have to add a 2 here. 2637, there we go. And this is 0.2733. Okay, and we're going to add that to 0.0096, and we get 0.2829. And then our final distribution amount, our third deviation away would be 0.2925, 0.2925. Now we're going to do the same thing, but we're going to go to the left. So we'll just say with 0.2637, 0.2637 minus 0.0096, and that would be 0.2541. And we're going to do is subtract again 0.0096, and that ends up to be 0.2445. And then one more time to get the third one on the left, and that's 0.2349. All right, and so now that's now labeled. Okay, so we mentioned this previously. Normal distributions are completely described by the mean and standard deviation. So the 68, 95, and 99.7 rule further reinforces this fact. This rule states, in a normal distribution, approximately 68% of the data lies within one standard deviation of the mean, 95% of the data lies within two standard deviations of the mean, and 99.7% of the data lies within three standard deviations of the mean. All right, so we can take a look at this chart and see that expressed there. Now, we can break this down a little further in that if we take this and we look here, 34% is going to be in this side and 34% over here, right? Half and half. From there, we can take from 95 to 68%, right? So that leaves 27%. So each of those two sections are going to be, this is going to hold 13.5% of the data here and another 13.5% of the data here. And then that last piece would account for 4.7% of the data, which, so each of those two pieces, this would be 2.35% here, and this would be 2.35% here. Okay. So consider your normal curve from item 2. All right, what proportion of the data lies between the two data points that were not identified as the mean? Okay, so we just did all that. Okay, so I kind of moved ahead, right? So from -1 to 1 is 68%. From -2 to 2 is 95%. And from -3 to 3 is 99.7% of the data. Okay, and we just completed the scale for that, right? All right, and between what two batting averages are 95% of the data and 97? So in that case, we come back up here and collect that and say between 0.2445, right? So basically we're just taking this scale that we already put here. All right, so let's go ahead and label this curve, which is identical to the one we did prior. Okay, we jumped the gun a little bit. 445 over here is 0.2541, 0.2637, that's our mean, right? 0.2733, 0.2829, and again 0.2925. Okay, between what two batting averages are 95% of the data? Well, so 95% of the data would be between 0.2445 4, 5, 2, 2, 8 to 9. And 99.7% of the data is going to lie between 0.2349 up to 0.2925. Alright, so what we would do here is what proportion of the St. Louis team batting averages for the year 1964 to 2013 is below 0.269. Okay, so first thing is, why is 67% the average of 50 and 84, one standard deviation above an incorrect response? Because the data itself does not necessarily coincide to that value. All right, we have to do what's called some calculations, right? So we just can't average those two values together, okay? Because it's a curve. It's not shaped like a rectangle, where if we just slide left and right, we can just add them and divide, okay? So it's because it's the shape of the curve. The shape of the curve. Okay. And because we are not taught how to find the area under a curve is done in calculus, so we don't know how to calculate the area under the curve. Okay, they do it in calculus using what's called an integral, and basically because they've taken those things and figured out how to find this, okay, we can basically go ahead and use what's called a z-score. Okay, so first thing we're going to do is we're going to find the z-score. Okay, so let's go ahead and calculate that. So the z-score is equal to, all right, and this is the symbols. Well, we'll just use the, in this case, it's going to be 0.269 minus 0.2637, and we're going to divide by the standard deviation of 0.0096. So we can pull up our calculator here and just plug that in. So it's 0.269 minus 0.2637, right? And here's what I should have done. I want to do my fraction, so it makes it easier. I can do just one calculation. All right, so alpha y equals number 1. So 0.269 minus 0.2637, and we're going to divide that by 0.0096. And I get 0.5520. Okay, so my z-score, rounding to the nearest hundredth, is 0.55. Okay, so on the standard normal table, let's find this. So here we'll see a copy of the standard normal table. So we're going to work down, we're looking at the z-score, and it's 0.55. So we come down here, and then we've got 0.5, and then we come over to this column, and it's 0.55 is right under here, right? 0.7088. So that is what our z-score leads us to find. Okay, so this would be 0.7088. What that means is 70.88 0.88% of the data. Okay, so that's why we just can't add those two values together and divide by 2. Okay, so that's why we use the z-score. Okay, so let's take a look at the calculator here and go ahead and do the same work. Okay, so we're going to come over here and we're going to go to the stat button and we're going to go to tests, and here's the z-test. Okay, all right, and since we're already using we already have the stats, so we're going to input this. Okay, so this symbol here is called mu, and mu is the value that we're looking for. So in this case, that's 0.2637. The next number is sigma, and that's the mean, or excuse me, standard deviation. Mu is the mean, sigma is the standard deviation, 0.0096. Okay, x bar is what number are we looking from. So this would be 0.269. And this n value is the maximum. Well, the highest value you can possibly have as a team batting average, even though it would never happen, is 1, right? 1,000 batting 100, right? So they say batting 1,000. So this would be 1. Okay, and we're looking at this going to the left. Okay, so we want to highlight enter there, and we're just going to calculate it right now. All right, so we come back and we have this value right here. Okay, so okay, hold on, there we go. I'm going to put this up here. All right, so there is our calculator information. So you'll notice it's 0.70955. Okay, we're off just a little bit, all right, from what we calculated on the other one. And the reason for that is this right here. Okay, the table only went to 0.55. The calculator goes all the way out here. Okay, so this would be 0.7095, which translates to 70.95%. So that's not far off from our other answer that we got from the standard normal table. Matter of fact, that's a small discrepancy. I mean, it's minimal difference. Okay. All right, so from here you'll see we have lesson practice. So you go ahead and work on that, and we'll see you next time. Peace.